we'll get started. So, we want you to have our master demo man, Dave, back. Dave's going to provide some nice real-world examples of some of the things we've been learning the last couple of days.
Okay. This morning I'm going to do a few demonstrations that center around Faraday's Law of Induction. Yeah, I think you've all covered that already. And Lenz's Law, which is that negative sign that shows up in Faraday's Law. And hopefully this will help you understand that a little bit better. You know, this idea of induction and electromagnetism in general is a pretty important concept. You know, a lot of all of the electrical devices that we enjoy today, many of which were not around when I was younger, are based on understanding these principles. If for some reason we were living in a bizarro world where electromagnetism and induction did not exist, you'd be talking to your friends not on a cell phone, but through a soup can connected with a string. Okay? So this is pretty important stuff. And it extends across disciplines, probably much more than you might think. So the first demonstration I'm going to do involves what we call a physical pendulum. And this one is simply a sheet of brass hooked to a pivot that can swing freely back and forth, as you can see. Brass, of course, is a non-ferrous material, which means it will not stick to a magnet. And what I'm going to do is I'm going to move this pendulum over so that it can swing freely between the poles of this relatively strong magnet. Okay, so the magnetic field is pointing either towards you or towards me. I'm not sure which. It doesn't really matter. Okay, so I'm gonna reproduce what I did out here. Does anybody have any insight as to what might happen when I do that between the poles of a magnet? Any other ideas? All right, why don't we do it and see what happens? Okay. But that slows down rather quickly compared to what was going on out here, right? So he was on the right track. Picture this. Imagine in this plate electric currents being induced by the field of the magnet. Okay, and where he was going, and correctly, was that those currents are induced in such a direction so that the magnetic field that moving current generates. Remember, all magnetic fields are the result of moving charges. Okay, so the magnetic field associated with that current in this plate always produces a field that opposes the one that induced it in the first place. Okay, so those two fields, just like pushing the two same ends of a magnet together, they work against each other. Okay, and what if I were to take this solid plate off and put this one on? It's exactly the same material. Only can never do this quickly while I'm talking. Only it has slots in it. Can everybody see the slots? Okay, there's vertical slots cut in this one. And again, it swings very nicely out there, okay? What's going to happen relative to the solid one now when I swing this? By cutting, if we imagine current loops in this piece of plate, right, and correctly, and if we imagine current loops in this plate, what can you say maybe about the current loops that are induced in this plate relative to this one? Remember, we cut slots in here. Can they be as big? No, you can kind of imagine a loop, say, going, covering most of the surface area. But with this one, that's not quite true because there's slots cut there. So we're going to restrict the way that the current can flow inside this particular plate. So let's do that. There's really not a whole lot of difference between one with the slots in it and one with the plate. Okay? And if any of you have ever taken a power transformer apart and wondered why the core is laminated, this is why. Because any induced currents in the core of a power transformer are losses. And that's more money you pay to the electric company. Okay? All right, any questions on that?
Has anyone actually taken a transformer apart before?
Does anybody know what a transformer is? Not the toys. You never taken it? He's a theorist, that's why. Well, if you get to that, we do have one cut in half in the back. Transformers are everywhere. You know, those are those usually heavy iron core things with wire wrapped around them. You see one in your microwave oven if you ever take it apart. Older TVs, the big gray things that are hanging on the power pole, those are transformers. And we'll talk a little bit more about that in a bit. Okay, so along the same lines, again, this is exactly the same thing that's going on with the previous demo. This time I have an aluminum tube that's hollow. It's got a fairly thick wall, okay? And what do you suppose, this is an aluminum slug. Again, aluminum is not magnetic, okay? It doesn't stick to a magnet. What do you suppose is going to happen when I drop the aluminum slug through the pipe?
Slowly.
What? Up, down, stay the same? No, those are wrong. That's a different set of demos. Well, it's going to fall, right? Where'd it go there? Just like dropping it outside the tube, okay? Nothing's going to happen, really. I just used that to show you that the tube's hollow and that nothing happens. Okay. So it takes about the same amount of time. What if I take my magnet and do that? This is a very strong neodymium magnet.
Slower.
What's that?
It's going to be slower.
It's going to be slower. Why is it going to be slower? Same as the last one, different shape.
It's inducing a current in the hollow tube.
Right. You can actually picture, it's not hard to imagine this tube as a stack of many, many very thin washers, right? So as the magnetic flux increases through that first ring, if you will, it's going to induce a current, and that current is going to be in such a direction as to oppose the field that produced it. So this is going to see a force up, right? What happens when it gets down here? Now the field that's above the magnet, cutting that same ring, the flux is going to be doing what?
Pushing it down, decreasing.
Decreasing. So the current that's induced in that upper ring and the ones beneath it that are above the magnet is going to be in such a direction as to increase the flux because it sees it decreasing. Remember, it always does the opposite, right? Kind of like children. So that means that this is going to see a force pulling it back this way as well. So as this falls, it's going to feel a force pushing up and pulling. Okay, let's see what happens. Could order pizza at the time it took that. Pretty impressive. All right. Any questions on that? Yes.
Will it shock you?
Will it shock me? No. So again, same as the last two. This time I have a thick block of copper. And again, another really strong magnet. Okay. This one happens to be rectangular shape. Okay. So what I'm going to do is I'm going to take the magnet and I'm going to drop it on the plate. Okay. This time I'm just going to do it. Is that expected? Yeah?
No.
No? You expect it kind of at this, because this is kind of repetitious by the third time, right? Everything slows down. Okay, same thing. We're inducing big currents in there. They oppose the magnet, the field that produced it in the first place. Okay, theoretically, I can drop this from as high a height as I want and have the same thing happen. The trick is dropping it so it's flat. If I drop it cockeyed, it'll chip a corner of the magnet. Okay. molasses or syrup. Not that you do that much, but you can kind of imagine. In fact, you can see the copper shifting as I try to move the magnet quickly over the surface. Okay?
So imagine if you could get that block of copper and you could make it such that there's no resistance and the currents basically required almost no energy to move around. So that would be what a superconductor is. A superconductor is material that can have like that resistance. Then you can basically get that resistive force upwards for free. And that maglev trains would so we're talking more about superconductors. That's the ultimate goal of this type of thing for technological use would be to have a chunk of titanium.
Did you say unobtainium? You did say that, okay. For those of you who are behind in your movies, tough luck. Okay. All right, so now we're going to move on. And in the previous 3 demonstrations, I used a permanent magnet, okay, which you're all familiar with. This time we're going to use an electromagnet for the next demo. And this is about 140 turns that's plugged directly into the AC outlet, okay? And the type of current that you can get in your house and from these outlets is called alternating current, okay? So this is switching directions once every 60 hertz, or twice every cycle, the 60 hertz cycle. So on the first half cycle, it's going in one direction, and then it switches and goes in the other direction on the other half of the sine wave. Okay. Don't try this at home. That particular frequency and the currents involved, your heart really doesn't like that. So you gotta be careful with alternating current. Mostly it's due to the frequency. Okay, so I got a button down here that if I hit, I can energize the coil. And you can hear the current, that's what we call 60 cycle hum. Sometimes your lights do that if you're near a big power transformer or you're trying to steal copper from the substation. Not a good idea, by the way, when it's humming like that. That's the current going through there. And I'm going to take my big magnet, I'm going to set it next to it. And you'll see that there's indeed a field that's trying to flip this magnet over, only it's changing very, very quickly, so it doesn't really have time, so it just kind of rattles. Okay? Put this in the safe. I got too many magnets here. I'm going to get in trouble. All right. So here I have the next piece of aluminum non-ferrous. This one happens to be donut shaped, and I'm going to take that and set it on top of the electromagnet. And when I energize the field, you expect what to happen inside the ring. Everybody should have this. Going to induce a current in the ring that's going to have its own associated magnetic field, which in turn is going to oppose the one that produced it. And if it opposes the one that produced it, you expect a force. Right? Okay. So here, remember what I was talking about laminated cores and transformers? This is a laminated core of soft iron wires that are just held together with a tube. I'm going to put my donut-shaped electromagnet on top of the iron wires. What does the iron add to this? Anybody have any ideas? No one's ever made an electromagnet out of paper clips, a nail, 2 wires, a wire, and a battery. Yes, thank you. You don't do that anymore. Kids don't do that anymore. If you ever get the chance, take an iron nail, a battery, magnet wire, which is or some insulated wire, wrap it around the nail and just hook it to the terminals and pick up some paper clips with it. It's an electromagnet. Okay? Iron concentrates the magnetic field, much like a lens can focus light. That's kind of a loose analogy. Okay? So if I put this on an iron core, I'm generating the same field because the current hasn't changed, but I'm concentrating it through the center of the ring. So we expect a bigger effect, right? And indeed there is. Okay. And because this is an alternating effect, that's that. Okay. And jumping ahead a little bit, this is what I mentioned previously. This is a model of a simple power transformer. Primary, secondary. Here's your house running light bulbs. No touching, no hands. Just coupling between the changing magnetic field. Okay. This is a 12-volt light bulb. So the ratio of the windings here to there is about 12. Okay. That's how the dangerously high voltage and currents on the overhead power lines are transmitted to somewhat less dangerous voltages and currents in your house. Okay? All right. So, running out of space. Okay, so we can do one last thing with this particular demonstration. And we can take our ring and we can change its temperature. Okay? So this is liquid nitrogen. It's 77 Kelvin, which translates to what in Fahrenheit? I can't remember either. It's like minus 350. I can never remember the conversion. I used to know it when I was a student, but since I don't have to know it, I don't know. No, it's really cold. I mean, coldest we see in Vermont here on a real bad night is like 40 below. I've seen a few of those. So this is a good 300 degrees colder than that. Okay. So I'm going to take the ring and I'm going to put it back on the post. Okay. And what do we expect to happen to the effect? Less, more, stay the same? More? A lot more? Your car doesn't start very well in the winter. Cold, battery, electrons. Electrons must be slower in the winter, is that right? Battery? Oh. So how many people think it's going to stay the same? More? More? Less? A few less? Okay. Not as convincing as the audio vote, but okay. So, okay, we come down to temperature, and I'm going to put that on the post. Watch real careful. Okay, so the Moors have it. Don't do that at home. We'll do it once more because it's fun. It's either that or lecture. Yeah, that's good. This is good stuff. I think you mentioned something about the relationship between temperature and resistance, did you, before? Okay. That's what you see, okay? You drop the temperature, the resistance goes down, same field, you can induce a much bigger current. A much bigger current means a much bigger field. I think once in about, Mark? I'm not going to tear this down over here. I think it was, I think once in about, I've been here, I don't know, 25, 30 years, I've broken a light. Since they renovated, they don't line up right. Anyway. Okay, let me with this. One last thing. I know you're dying to get to lecture. Okay, this last demonstration is a combination of kind of everything you've seen, or actually it's a more dramatic demonstration of the same thing. This next device you can think of as, this thing I just did is called a jumping ring. This next device is actually, you can think of it as two of those jumping rings, end to end and horizontal. Okay? So what we're going to do, and I'm going to explain this as I try not to forget an important step. So this consists of a coil of about 5 turns of wire that is in turn hooked to this capacitor bank on the second level. Right here, the first level is a high voltage power supply. On the top is a gravity switch right there that is opened by this weight. When that's open, The power supply is free to charge the capacitor. When it's closed, it disconnects the power supply and discharges the capacitor to the coil. Very simple circuit, okay? Inside the coil, I'm putting an empty soda can. And I'm going to start the charging process now. Okay. So this is going to take a little while to charge because the power supply can only dribble so much current into the capacitors. You can kind of think of this as filling a big 55-gallon drum of water with a smaller bucket. It takes a little bit of time. Okay. So these lights are for your amusement. It's basically equivalent to 1,000 volts per LED. When it gets up around 10, that means we're up to the right voltage. I've got the official meter back here that I'm watching. So when we dump all this energy through that coil, there's going to be a huge current, tens of thousands of amperes over a very small amount of time. That in turn is going to induce a high current in the can. And much like, now when you saw that ring jump, if you analyze that jumping ring with your right hand rule and look at the components of the magnetic fields, it's pretty easy, it was obvious that there was a force up on the ring, but what wasn't so obvious was a radial force inward on the ring, okay? Because that ring's very stiff. Now in the case of the soda can, that's not true. And here's an example of a bunch of soda cans that were in this device at various voltages, okay? This is a lower voltage, higher, progressively higher, and all the way up to 10,000 volts for the short can here, okay? So you can see this, the can starting to neck in. That's that radial force inward, and this separation of the can is that jumping ring effect that you saw. Only this can's going to feel it pulling on both sides because the loop's in the middle, and it's going to crush it in, okay? So instantaneously, in fact, this can is going to heat up, and some of that aluminum is actually going to melt, okay? And you'll see some smoke, and that's the sugar, or what passes for a sugar substitute, burning off the inside of the can. And we're up to a little higher there. So we're up to about 5 kilovolts. These are 10 kilovolt capacitors, so we don't want to overcharge, over voltage a capacitor because they like to blow up when that happens. You know, everybody always asks that. I didn't expect you to ask it. That's anyway to make me feel better about what I just said about not over-voltaging the cap. This is an analog voltage meter. They can stick. So I don't want the needle to stick in a spot and then have the voltage go too much higher. So I grew up with an old TV, and most of you probably never had that privilege of learning that if you bang on the side of the TV, especially in rural Vermont in the 70s or 80s, the reception gets better. And the TV acts normal. Anyway. What's that?
On this side, all the lights are on.
Yeah, I told those are for you. I don't care. That is actually monitoring the line voltage and not the charging voltage. So it's a little bit off. Okay, we're up to about 8,500. Oh, by the way, this is going to be really loud, so you want to stick your fingers in your ears when I give you the high sign. The kinetic energy, 10,000 joules, 10,000 volts with these capacitors is roughly the equivalent of a rifle bullet, the kinetic energy of an average rifle bullet. Okay, up to 9,000. Done. I'll pass these cans around, the pieces, and watch the sharp edges, but you should be able to feel that it's still warm. Okay, you want to be warming up your fingers. All right, here we go. any of those, yeah, just pass it around. Feel free. By the way, 10 cents. Like that old Seinfeld episode. No.
Only in Michigan.
Oh, wait a minute. Well, I got 2 5-cent halves. So. All right, I'm done. That's a little longer to shoot. All right, any questions before you have to do the lecture?
Can we do more?